Welcome back to Revise and Resubmit, the podcast that takes, those really dense academic papers and makes them surprisingly interesting. I'm Pavlov.
And I'm Nikita.
All right, everyone, get ready, because today we are going deep into quantum computing.
Oh, yeah.
Microsoft just made a huge announcement.
Yeah.
Majorana 1.
Big stuff.
A quantum processor running on something.
That's right.
Called topological qubits.
Yeah, we've got their blog post laying out the big picture.
Wow.
A Nature paper detailing a key experimental breakthrough.
Really exciting.
And even a roadmap on arXiv hinting at where they're headed.
So where are they headed with all this?
Ambitious.
Yeah.
To say the least, they're talking about scaling up to 1 million qubits.
Wow.
On a single chip.
Okay, so before we get too far ahead of ourselves.
Yeah.
What exactly is a topological qubit?
Right.
And why is Microsoft so hyped about them?
It all starts with this brand new material they've engineered called a topoconductor.
Okay.
Imagine a superconductor.
Okay.
Where electrons pair up and flow without resistance.
Right.
Now, tweak that material in just the right way under specific conditions.
So we're talking crazy low temperatures and precise magnetic fields, right?
Precisely.
Like colder than outer space kind of stuff.
Colder than outer space, and what emerges at the ends of these specially tuned nanowires are Majorana zero modes, or MZMs.
MZMs.
Think of them as quasi-particles.
Interesting.
Not quite particles in the traditional sense, but exhibiting unique properties.
Okay, so these MZMs are the heart of topological qubit.
Mm-hmm.
But how do they actually hold quantum information?
It's not through energy levels, like in conventional qubits, but through something called parity.
Parity.
It comes down to whether the wire has an even or odd number of electrons.
Got it.
Now, in a typical superconductor, any lone unpaired electron stands out.
Makes sense. Everyone else is coupled up.
Stands out like a sore thumb.
Right.
But in a topoconductor, that lone electron gets shared between two MZMs at the ends of the wire.
Interesting.
It becomes almost invisible to the surrounding environment.
So the information is encoded in this invisible shared state.
Right.
Making it incredibly stable.
Exactly. This invisibility is what gives topological qubits their inherent robustness.
Wow.
They're protected from the kinds of noise that plague other qubits.
Yeah.
Making them potentially far more reliable for computation.
That's the theoretical beauty of it.
Yeah.
But how do they actually control these qubits?
Right.
That's where this Nature paper gets really interesting, right?
Yeah, absolutely.
They've actually built a device to measure the state of these topological qubits.
Right. They've created an interferometer using a superconducting nanowire coupled to quantum dots. The key here is that they can measure a property called quantum capacitance, which changes based on the number of electrons in the wire.
Well, capacitance is like how much electrical charge something can store, right?
Exactly.
But what does that have to do with the qubit state?
Remember, the qubit state, its parity is all about whether the wire has an even or odd number of electrons. That single unpaired electron, or the lack of it, directly affects the quantum capacitance of the dot.
Ah, I see.
Yeah.
So by measuring the capacitance, they're indirectly detecting the presence or absence of that crucial single electron.
Right.
Which tells them the state of the qubit. It's like an electron fingerprint.
That's a great analogy. It gives them a way to read the information encoded in the MZMs without disturbing their fragile quantum state.
Got it.
And this measurement ability is a key building block for Microsoft's grand plan.
Which is to scale up to 1 million qubits.
Right.
Using these tetrons they've outlined in their roadmap.
Exactly.
What is a tetron and how does it fit into the bigger picture?
So imagine two of these topological wires, each with their MZMs placed parallel to each other.
Right.
And connected by a regular or trivial superconducting wire.
Okay.
That's your basic tetron.
So it's like a double wire setup for a single qubit.
Yeah.
Why the added complexity?
Because this arrangement allows them to do
specific kinds of measurements that are crucial for controlling and entangling qubits.
Got it.
They're laying these tetrons out in a 2D grid, forming the foundation of their architecture.
So the tetron is the building block, and the 2D grid is the blueprint.
Exactly.
But how do they actually perform computations using this setup?
It's all about carefully choreographing a sequence of measurements
Interesting.
on these tetrons.
Okay.
By measuring different combinations of wires and quantum dots, they can effectively steer the system toward the desired outcome.
So instead of directly manipulating the qubits with lasers or microwaves,
Right.
they're using measurements to guide the computation.
Yes.
That seems fundamentally different.
It is, and it plays to the strengths of topological qubits. Remember, they're inherently more robust.
Yeah.
And this measurement-based approach further minimizes disturbance,
Right.
leading to potentially higher fidelity operations.
It's a pretty radical departure from the status quo.
But the real question is, can they pull it off?
Right.
Their roadmap lays out some ambitious milestones.
It does, and it's going to be fascinating to watch how it unfolds.
Yeah.
They're starting with demonstrating entanglement between tetrons, then moving on to more complex manipulations called braiding transformations.
Colon braiding transformations?
Yeah.
That sounds like something out of a sci-fi novel.
Right.
What exactly does that involve?
Imagine those MZMs
Yeah.
as beads on the wires.
Oh.
Braiding involves carefully moving these MZMs around each other,
Right.
swapping their positions in a specific sequence.
And this dance of the MZMs allows them to perform computations.
Yes.
How does that even work?
It's a bit mind-bending.
Yeah.
But the braiding operation actually changes the way the qubits are entangled, effectively implementing logic gates.
So it's like a quantum ballet where the choreography dictates the computation?
Exactly.
That's wild. But even with these robust qubits, aren't errors still a concern?
Absolutely. No system is perfect.
Right.
That's why their roadmap also includes developing and implementing quantum error detection schemes.
Okay.
It's going to be crucial for ensuring the reliability of their computations.
Seems like they're really thinking long term,
Yeah.
building in fault tolerance from the ground up.
Uh-huh.
And it seems like DARPA has taken notice.
Absolutely.
Being selected for the final stage of their US2QC program is a pretty big deal.
Right. It is. DARPA is all about
Yeah.
pushing the boundaries of what's possible.
Right.
Their focus is on utility-scale quantum computing,
Meaning
getting systems that can solve real-world problems beyond the reach of classical computers.
Got it.
Their endorsement is a strong signal that Microsoft's approach is on the right track.
It's clear that Microsoft is playing the long game here. They're not just trying to build a quantum computer.
Right.
They're trying to build a quantum supercomputer.
A quantum supercomputer.
What are the implications of that? What could a million qubit machine actually achieve?
That's the million-dollar question.
Literally.
Literally and figuratively.
And figuratively.
It opens up a world of possibilities that are hard to even fathom right now.
Yeah.
We could see revolutions in fields like medicine,
Wow.
material science, artificial intelligence.
It's almost too much to wrap our heads around.
It is, but that's what makes this so exciting.
Right.
We're witnessing the birth of a new computing paradigm.
Yeah.
And Microsoft is pushing the boundaries further than anyone thought possible.
Okay, before we get too lost in the future,
Yeah.
let's dig a little deeper into the present.
Okay.
That Nature paper goes into some detail about their experimental setup
Right.
and the results they achieved with their single-shot parity measurement. Let's unpack that next.
Absolutely. Let's look at how they actually built a device to measure these elusive MZMs and what their findings tell us about the potential
All right, let's dive in.
of topological qubits. So this Nature paper, it's all about proving they can actually accurately measure the state of a topological qubit. And they did this by building a device that's incredibly sensitive to the presence or absence of a single electron.
We're talking about detecting a single electron here.
Yes.
That's mind-bogglingly small.
It is.
How do they even achieve that?
It comes down to a clever technique called dispersive gate sensing. They've got this superconducting nanowire coupled to a quantum dot forming an interferometer.
Okay.
Now, by using a radio frequency signal to probe the quantum dot, they can detect tiny shifts in its quantum capacitance.
Oh, so capacitance is like how much electrical charge something can store, right?
Exactly.
But what does that have to do with the qubit state?
Remember the qubit state?
Yeah.
Its parity is all about whether the wire has an even or odd number of electrons.
Right.
That single unpaired electron, or the lack of it, directly affects the quantum capacitance of the dot.
So by measuring the capacitance,
yes,
they're indirectly detecting the presence or absence of that crucial single electron.
Right.
Which tells them the state of the qubit. It's like an electron fingerprint.
Precisely.
Oh.
And they achieved a remarkably clear signal, too.
Really?
At optimal conditions, they could determine the qubit's state, its parity, with a signal-to-noise ratio of 1.
Wow.
In just 3.6 microseconds.
The signal-to-noise ratio of 1 in microseconds.
Yes.
What does that actually mean in terms of reliability and speed?
It means their measurement is both fast and accurate. The signal stands out clearly from the background noise.
Okay.
And that speed is crucial because remember, qubits are notoriously fickle. They tend to lose their quantum properties over time.
Right. It's like they have a limited shelf life.
Exactly.
Before they become ordinary bits.
Right.
So being able to quickly measure them is key to harnessing their power before they decohere.
And this experiment demonstrated that not only can they reliably measure the state of a topological qubit, but they can do it fast enough to potentially outpace decoherence.
That's a major win.
It is.
For their approach.
Absolutely.
Now, I understand they also use something called the topological gap protocol in their experiments.
Yes.
It sounds like they're trying to tune the system into a sort of sweet spot.
That's exactly what they're doing.
Oh.
Remember how we talked about the topological gap? That energy barrier that protects the quantum information?
Yeah.
Well, it turns out that this gap can vary.
Really?
Depending on the condition.
So it's not a fixed shield, its strength can fluctuate.
Right. This protocol is all about finding the ideal combination of electron density in the nanowire and the applied magnetic field that maximizes the topological gap.
So it's like fine-tuning the system to achieve the strongest possible protection for the qubit. Makes sense.
Yeah.
Now, all of this is impressive.
It is.
But Microsoft's real goal is to scale this up.
Right.
How do they go from a single tetron in a lab to a million-qubit supercomputer?
That's where their roadmap on arXiv comes in.
Go.
They've outlined a clear path forward, starting with proving they can entangle qubits across multiple tetrons.
Entanglement, that's the spooky action at a distance thing, right?
Exactly.
Where two qubits become linked, even if they're far apart.
It's one of the defining features of quantum mechanics and a key ingredient for powerful quantum algorithms.
Right.
Once they can reliably entangle tetrons, they'll move on to demonstrating these braiding transformations we talked about earlier.
Right, the quantum dance of the MZMs.
Exactly.
But how do they actually control these braiding operations on a larger scale?
It comes down to those precise measurements again.
Okay.
They'll use different configurations of measurements on the tetrons to effectively move the MZMs around each other, weaving them into specific braiding patterns.
So it's like a quantum choreographer dictating the steps of the dance through measurements.
That's a great way to put it.
Yeah.
And it's potentially much more robust than trying to directly manipulate these fragile qubits with lasers or microwaves.
Yeah.
But it's also incredibly complex.
I can imagine.
They'll need to develop sophisticated control electronics and software to orchestrate all these measurements with exquisite precision.
It sounds like they're essentially building a new type of computer from the ground up.
You could see that.
With its own unique programming language and control systems.
It's not just about the hardware, it's about the entire ecosystem of tools and techniques needed to program and control these topological qubits.
It's a massive undertaking.
It is.
But the potential payoff is huge.
It is.
If they can pull this off, it could revolutionize entire industries.
It could.
But let's not get ahead of ourselves. What are the next steps in their roadmap?
Well, after they've mastered entanglement and braiding, the next big hurdle is quantum error detection.
Right. Even with these robust topological qubits, errors are inevitable in the quantum world.
Absolutely.
How do they plan to tackle that?
They've outlined a strategy for implementing quantum error correction codes that are specifically designed for their tetron-based architecture.
So it's like building in a self-healing mechanism, constantly checking for errors and correcting them on the fly.
That's the idea. And they'll need to prove that these error correction schemes work effectively as they scale up the system. It's going to be a critical test of their approach.
It seems like every step in this roadmap is a monumental challenge.
It is.
But you can feel the excitement in their writing.
Absolutely.
They really believe they're onto something big here.
They do, and their confidence is infectious.
Yeah, it's remarkable that they're tackling this problem from all angles, from the fundamental physics of topological materials to the engineering of scalable architectures and error correction codes.
It's a truly holistic approach.
It is.
Which is probably why DARPA is so interested. They're not just throwing money at a trendy technology.
Right.
They're investing in a team that seems to have a clear vision.
Yeah.
And the expertise to execute it.
It's this combination of vision and expertise that makes this such a compelling story.
Yeah, we're watching a team of brilliant minds pushing the boundaries of what's possible, and the implications are staggering.
Okay, before we get too carried away with the what-ifs, let's take a step back.
Sure.
And consider the broader context.
Okay.
How does Microsoft's approach compare to the other players in the quantum computing race?
That's a great question.
Are they truly ahead of the game, or is this just a different path to the same destination?
Let's compare Microsoft's roadmap with the strategies of other tech giants vying for quantum supremacy. It's a fascinating landscape of different qubit technologies and architectural choices, each with its own pros and cons.
So we've got Microsoft betting big on these topological qubits, but they're not alone in the quantum race. What are some of the other horses in this derby, and how does their approach stack up?
It's a fascinating mix of strategies out there.
Yeah.
You've got companies like Google and IBM going all in on superconducting transmon qubits.
Yeah, I've heard about those.
Yeah.
They seem to be the most mature technology out there, right?
Definitely the most developed.
Okay.
They're relatively easy to make with existing tech.
Right.
And they've shown decent coherence times, meaning they hold on to their quantumness for a bit.
So why isn't everyone using them?
Well, they're incredibly sensitive to noise, which can throw off calculations.
Right.
Plus, scaling them up to the thousands or millions of qubits needed for complex problems is a huge engineering challenge.
So robustness versus scalability. It's a recurring theme in this quantum world, isn't it?
It is.
What about other approaches?
Yeah.
I've heard whispers about something called trapped ions.
Trapped ions. That's where you use lasers to trap individual ions, which become your qubits. They boast really long coherence times.
Wow.
And are well isolated from noise, making them very stable.
Sounds promising. What's the catch?
Scalability again.
Right.
Wrangling a huge number of ions with lasers is a logistical nightmare.
Right.
Plus, the whole setup is incredibly complex and expensive.
So it seems like every approach has its own unique set of strengths and weaknesses.
It does.
Where does that leave Microsoft with their topological qubits? Are they the dark horse in this race?
It's hard to say for sure.
Yeah.
They're definitely betting on a less mature technology, but the potential payoff is enormous if they can overcome those engineering hurdles.
Yeah.
Topological qubits could leapfrog the competition in terms of scalability and reliability.
It's almost like you're taking a different route to the summit of Mount Quantum.
That's a great way to put it.
Everyone's aiming for the top, but the paths are vastly different.
And it's important to remember that we're still in the early days of this expedition.
For sure.
It's possible that the winning approach hasn't even been discovered yet.
It makes you wonder, what does the summit even look like? What's the ultimate goal of all this quantum craziness?
Well, Microsoft talks about building a quantum supercomputer.
Yeah.
A machine capable of solving problems that would take classical computers billions of years.
Wow.
Crunching them down to hours or even minutes.
That's some serious computational horsepower.
It is.
But what kinds of problems are we talking about? Give me the wow factor.
Yeah.
The big world-changing stuff.
Imagine designing new materials from scratch, atom by atom.
Okay.
We could create superconductors that work at room temperature, revolutionizing energy.
Right.
Or super strong, lightweight materials for everything from aircraft to prosthetics.
We could literally build the future with this technology.
Exactly. And that's just material science. Think about drug discovery. Quantum simulations could model complex molecules and proteins, allowing us to design drugs with pinpoint accuracy targeting diseases at the molecular level.
So we could cure diseases that are currently considered incurable.
The potential is certainly there, and it extends far beyond medicine.
Yeah.
Quantum computers could revolutionize artificial intelligence, leading to breakthroughs in machine learning and problem solving. They could help us model climate change with unprecedented accuracy, guiding us towards sustainable solutions.
Wow.
The possibilities are truly mind-boggling.
It's almost overwhelming to think about the implications.
Yeah.
But amidst all this excitement,
Right.
it's easy to lose sight of the fact that this is a technology, a tool.
Uh-huh.
And like any tool, it can be used for good or ill.
Right.
How do we ensure that quantum computing benefits humanity as a whole?
That's the critical question, isn't it?
Yeah, it is. What are some of the key concerns we should be addressing?
Well, one concern is that quantum computing could exacerbate existing inequalities. If access to this technology is limited to a select few companies or countries, it could create a new digital divide, widening the gap between the haves and have-nots.
So democratizing access to this technology is crucial. What else?
Another concern is the potential for misuse.
Okay.
Quantum computers could be used to break encryption, leading to widespread security breaches. They could be used to develop new weapons, creating a new arms race.
Wow.
We need to establish safeguards and regulations to prevent these dystopian scenarios from becoming reality.
It's a heavy responsibility.
It is.
Shaping the future of such a powerful technology, it almost feels like we're writing the rules for a new world.
We are, in a sense.
Yeah.
And it's a world where collaboration and ethical considerations must be front and center. We need to bring together experts from diverse fields, scientists, ethicists, policymakers, and the public.
For sure.
Open dialogue and thoughtful deliberation are crucial for guiding this technology towards a positive future.
This has been an incredible journey.
It has.
We've gone from the nitty-gritty of topological qubits to the grand vision of quantum supercomputers.
Yeah.
And the ethical dilemmas they pose. It's clear that we're witnessing a pivotal moment in human history.
Right.
A technological revolution that could reshape the world as we know it.
It's a revolution that's still in its early stages, full of uncertainty and possibility. But one thing is certain, it's a revolution worth paying attention to.
And for our listeners, that's exactly what we encourage you to do. Stay informed, stay curious, and engage in the conversations that will shape this quantum future.
Because the future is not something that happens to us, it's something we create together.
And that's a wrap for this deep dive. We hope you enjoyed exploring the world of topological qubits and Microsoft's ambitious quest to build a quantum supercomputer. As always, you can find links to all the sources we discussed in the show notes, along with some bonus material on our website. Until next time, keep exploring and stay curious. And don't forget to subscribe to Revise and Resubmit on Spotify and Apple Podcasts for more captivating deep dives like this one. And if you're enjoying the show and want to support us in creating more insightful content, consider becoming a patron on Patreon. Every contribution helps us continue this journey of exploration and discovery. Until next time, keep those minds curious, keep questioning, and keep revising and resubmitting.